Yes, so hello everyone. Simone, I would thank, not you, Simone, the other Simone who is not here, for reminding me not to thank the organizers, because of course, so instead I will thank the other organizers. Yeah, so this talk is really about subtraction. I think it's the first talk really, I mean, we have seen, of course, applications of subtractions. So I decided to waste some of your time going through some general aspects. So after the introduction, you see I will go architecture and then engineering and then actually getting your hands dirty with bricks. And I'll probably not be able to say much here. I must also apologize to people who have already essentially seen this talk, which in a very similar form I've given several months ago, almost a year. But the main difference really is that that talk that I gave some time ago on a couple of slides had preliminary, and now it's not preliminary anymore, but that required a lot of things. And this is, most of this work is done in collaboration with Canon Milloy and Chiara Signorite, Paolo Torrielli, and Sandro Uccirati. Okay, so this is, I used to say this is where we want to go, right? It's this picture for me, it symbolizes the extreme complication of what we want to do at HC events. This is an Atlas event with 3 jets, but when you look at it in such an event display, you realize that there are many questions here, like, is this a jet or is this not a jet? And this is, of course, an ambiguous question. It depends on which algorithm you are using. Atlas classifies this as a 3-jet event, and we now actually have a code that would compute a distribution for this kind of events. Unfortunately, the code takes 100 million hours of CPU to produce some plots, and so I think that we still have a lot of work to do, although Michael would probably disagree with me. So, of course, you all know this, so go quickly. Suppose you want to do, say, TT bar plus jet, right? And this is a 2-loop correction, so it's a contribution to the next leading order for this process, and it's 1 over epsilon to the 4th. If you want to cancel that, first you have to include the 1-loop correction with 1 more radiation, and one of these 2 has to be unresolved. You integrate it out. So this has a 1 over epsilon squared from the loop, and then it has 2 divergent integrations, which give the other 1 over epsilon squared. And then, of course, you have stuff like this. So the 3-level production of 3 particles, 2 of which are integrated over, and this will have 4 integrations that will diverge. And we have extremely general theorems that says that everything at the end will be finite, but you have a lot of work to do. Much more than you would imagine. So when you say it like this, many people, including especially myself, have made the mistake of thinking this is going to be easy, right? Well, we know everything. It factorizes. We know all the poles, and then you put them back together, they will cancel. Yes. So several years ago, when I was in this position and I thought it was easy, or at least not so difficult, then I actually wrote a shopping list. So what would one want to have from an optimal subtraction algorithm at NLO? Wow. Now, of course, this is my shopping list. People in this audience will may free to disagree, and I'm sure some do. First of all, it should be completely general, right? We have all the ingredients, and one should be able to compute general infrared safe observables with, in principle, with an arbitrary numbers of final state patterns, subject only to the existence of the matrix elements. So somebody has to compute, right, the matrix elements first. We would like it to be exactly local in the Born phase space, which turns out not to be so easy. So for example, the antenna subtraction is not in principle exactly local and compensates for that in the present version by doing some azimuthal averaging. At least, you know, from my viewpoint, I would like to have something which does not depend on external slicing parameters, although of course there will be technical cutoffs, right? But those, I imagine you can put them 10 to the -9, forget all about it. Now, this is really my personal prejudice. I would like a complete analytical results for the integrated counter terms, which we have now for the final state. People disagree, but I emphasize that I should add one word here. So one should have complete, simple. analytical results. Because of course, if your analytical results are 50 pages of polylogarithms or 50 pages of elliptic polylogarithms, then it will be very expensive to actually implement. And of course, overall computational efficiency, which should include the interfacings to event generators and codes, matrix element codes, and all that. So what one would really like is a code, which in fact, without some of these, Massimiliano's code fulfills many of these points. One would like a code, a public code, in which the user inputs a process and observables and gets out a prediction. Of course, maybe the user in the meantime goes for a month on vacation, but after a month or two, the user should be able to get a result. So this wish list has been essentially accomplished at next reading order. There are many subtraction formalisms. The mostly used are Catani-Seymour and Frizione constant Signer. But there is a Nagy Soper with various modification, and Tanya is the R here, who has, and LASS is us, essentially. At next reading order, as you all know, decades of effort, plural, so this is now 20 years since this has been worked on by many people, some of which are in this room. Both with the slicing and with subtraction and with innovative idea, including treating directly Feynman diagrams with cuts and without cuts in a whole bunch, which is really interesting. And the latest is local unitarity. And we wanted to call this local analytic subtraction from Torino so that it would, the acronym would be LAST. So we are the last. So where are we? So these are the papers. I'm not going to talk about this, so I'm just sort of giving you a quick situation statement. We work so far with massless partons. We have a full-fledged subtraction formalism at next reading order, which is being numerically implemented. And here, when I say simple integrals, so I wanted analytic results, the integrals at next reading order, they are all gamma functions, okay? So seriously simple integrals, the kinematic dependency is logarithms. At next reading order, we are done with final state radiation, done analytically, so to speak, which includes a menu of things that one has to have. So sector functions for us, phase-space mappings, checks on the phase. This is an extraordinarily expensive step in our formalism, and all integrals are done. So of course, the next natural step is on the one hand, the numerical implementation, which soon will be underway, and the generalization to the initial state, which we know rather precisely what's going to happen. It requires work because one has to introduce more sectors but no new concepts, whereas of course it's going to be quite different if one wants to include massive partons. Very well. So architecture, this is the beautiful, one of the most beautiful architectural pieces I know. And this is much less beautiful. So let me walk you through what we normally do. I know you know this, but I want to make a point which is easily made if one starts from the beginning. So at next reading order, this is what you have. And both these things diverge. So this is the virtual, this is the real, this is the observable, which you expect to be infrared safe, and you have to take the limit after summing. That doesn't work because you absolutely need numerical integrations, and so you have to come up with a counter term, and this is the definition of a counter term. So you take the real matrix element, and you have an operator, which we call L1, which of course is a sum of terms. So this is going to be the sum of all the singular limits of the real matrix element, so a sum of collinear sectors and a sum of soft sectors. And then you're supposed to be able to integrate that over the one particle phase space. That will generate the infrared poles of the matrix element, of the virtual matrix element with a minus sign. And then you build this object, which you have been adding and subtracting the same exact quantity. And then this is finite in the n particle phase space, the poles have cancelled, and this is finite as integrable in the n plus one particle phase space. So you are done. And of course, I am heavily underestimating the difficulty of what I'm doing, because first of all, this object you have to construct. You have a lot of freedom. It has many pieces, even next to reading order. And here I have a phase space, which is actually a ratio of phase spaces. So I have to integrate the single particle, but of course the single particle in the original phase space is tied up with all the others. There is a delta function. So you have to reparameterize phase space in such a way that the Born phase space factorizes exactly, and then you can do the integral on the other variables, right? So this is non-trivial, it requires mappings. Excellent. This is about the definition of L1, just to give you an example for us, and I don't want to dwell. So the way we do it is with sectors, which means that we define sector functions, which are a partition of unity. We define soft and collinear limits, which are Taylor expansions, Laurent expansions in the normal variables corresponding to the singularities. We require that these sector functions obey certain sum rules because we never want to integrate over sector functions. So we always want to work with combinations in which the sector functions sum to 1. And you have to find sector functions which obey these requirements. And here they are. I don't want to spend time on this. And then you see that for us, this L1 is actually a sum of many terms. In each sector, there is a soft singularity, there is a collinear singularity, and there is a soft collinear overlap. And usefully, as I believe was first pointed out by Massimiliano and Stefano Frixione many years ago, maybe 20 years ago, actually, or something like that. So then the subtracted matrix element, you really write it as 1 minus S, 1 minus C times the matrix element. So 1 is then the original matrix element, and this is minus all the singularity. Which is a sort of a nice way to visualize what is happening. Then the other thing that you have to do is forget it. The other thing that you have to do is, no, okay, I'll try my best. The other thing that you have to do is do this remapping at next to reading order. You can use Catani-Seymour, and then you see what is happening. Here I'm calling them bar limits. I will then not have the bars anymore, but now the Born matrix element is really in an n-particle phase space, and all the variables that you have to integrate over are sitting outside. And now, only now, you can really do what I had in the previous slide. Well, let's continue. This is far from trivial at next to reading order, okay? The one needs a menu of remappings, and one has to check their consistency, and it's very, very heavy work, in part discussed by Del Duca and Leonetti in that paper. So at next to reading order, now we are getting to the main point that I want to make. Of course, you have the sum of 3 pieces, and then you ask yourself how many counter terms do you need, right? So let's begin with the third line here. So you have the double real matrix element. You want to subtract all the single unresolved configurations. Then you also want to subtract the double unresolved configurations, but they have an overlap, right? The single unresolved are contained in the double unresolved. So you want to add back the strongly ordered configuration, which exactly extracts the overlap of these two. So I need an L2 operator, and then I needed the action of L1 on L2. We construct all these so that they are all commuting. And then you also need L1 on the real virtual here, right? So there are 1 counter term function in next to reading order, 4 functions at next to reading order. And then you integrate them in the appropriate phase spaces. And the rule is that you always integrate only over the most unresolved particle, unless, so if it's 2, you integrate over 2, but anything which has a 1, you integrate over 1, and you put them back, right? So this is now manifestly integrable in n+2. And this is where the delicate point is, right? So the fact that this integral will cancel the poles of this guy is a theorem. So this is just the general cancellation theorem, as you can easily convince yourself. This thing will cancel the phase space singularity of that by design. This thing will cancel the phase space singularities of that also essentially by design, and this is a general fact. So you are left with the fact that this is a sum of 2 counter terms which have a lot of arbitrariness, and they are affected differently by the phase space mappings. So it's not a theorem that the poles will cancel here, okay? It's not a theorem. So you have to adjust so that they do. And in particular, you can manipulate the real virtual by adding some poles that don't have phase space singularities, because otherwise you have a problem. And this is working by hand to some extent. And the rest of what I'm going to say is how trying to avoid working by hand in this case. And if you have fixed this line and this line, then this line will fix itself by the general theorem that the poles must cancel. So great. Now, we have thought for a while about how this generalizes. People are starting to talk about next cube LO subtraction. And this is what happens at next cube LO. So it's fairly easy to understand if you, I mean, it takes some time, but if you have the triple real, then you subtract the single unresolved, and then the double unresolved, and you put back the strong ordered, and then you have the triple unresolved, and then there are things that can go at different speed, right? So you can have one particle much more unresolved than the other two, or two particles much more unresolved than the third, or they can be strongly ordered, all three of them, right? And then if you look, and then of course you replicate the next to leading, the next to leading order plus poles here. So the RRVs are like one loop less, 1, 2, and 1, 2. And here you have the double virtual one real, which has a single counter term function and replicates the one loop calculation. So this is 11 functions, okay? It's 11 functions, out of which 5 are now strongly ordered in one way or another. And you can, I mean, one could write a formula for NKLO, right? It's just invent some notation for fancy combinatorics. You can do it, and what happens is that you find that the number of functions that you need is 2 to the k plus 1 minus 2 minus k, which is 1, 4, 11, 26, 57, and we'll never go there, so we don't need to worry. But one important fact is that strongly ordered configurations become more and more important. So we need to be, and also they are the ones that are not automatic. So the fact that in here there will be pole cancellation is not automatic, and we would like to understand and make it as much automatic as possible. So for that we need some engineering. This is, by the way, how the dome of Santa Maria del Fiore was actually built, which was a secret for 500 years. And then some Princeton people sort of figured it out together with some other people somewhere else. And the approach that we take, which is a bit orthogonal to our actual subtraction, is a top-down approach. So here I just want top-down, I mean we start from the virtual, okay? And from the virtual, this was discussed by other people, we know that we understand the virtual poles extremely well. They factorize in this exact way, and this Z factor here actually has structure, and it is, the product of jet functions times soft, subtracting out the soft collinear part, okay? So this is this Z, and importantly, all of these objects are defined in terms of matrix elements of gauge invariant operators, or suitably gauge variant operators, and so you can work with them to any orders. They are all known to 3 loops, so we really know this stuff extremely well, right? Whereas the real radiation we know considerably less well. But then what you start thinking is, okay, so if I know the virtual poles, can I build an object that is finite, just canceling the soft and separately canceling the collinear and separately canceling the soft collinear? And of course you can. It's rather simple, in principle. So you have an amplitude, you square it, and if you want a real radiation, you just allow it, right? And then this becomes, when you sum over the states, a total cross-section in the soft sector, which is finite by power counting. And then if you fix all the quantum numbers on the cut, those will be local counter terms, and the same happens for jets. We have the virtual poles, and so we square the object in a suitable way. Here you have to take a Fourier transform, and then this is finite because it's the discontinuity of a 2-point function, and then when you fix all the quantum numbers of the particles on the cut, you get a counter term, and this you can sort of see here. So this is the radiative soft function, or iconal form factor as we call it. It's the same thing as the soft function for the virtual, but it has particles, gluons or quarks in the final state. This defines the soft currents at whatever perturbative order, and if you compute, you reproduce the results of Stefano Catani and Massimiliano, and you can, if you want, go forward. And this is sort of the object which is supposed to be responsible for all the soft singularities, both in the sense of poles and in the sense of radiation, although this is actually not a theorem. And then when you square it, then this is the squared matrix element, you get something like this. So matrix element times complex conjugate. And this is the thing that if you sum over number of particles and integrate over the phase space, will give you a finite quantity. So it means that these are correct soft counter terms, because when you combine them with the virtual at the order you want, then you get a finite result. And we call this thing, for historical reasons, a completeness relation. So in the sense that I'm just putting a complete set of states in the middle. So this is the way we construct counter terms, and because of lack of time, I won't run you through the collinear, which is the same basic idea. And at next to leading order, in this top-down approach, you see that I literally start with the virtual amplitude, which I expand there. So it's 3 level, 1 loop soft, 1 loop hard, 1 loop collinear minus superposition, plus corrections. I square it, I construct Vn. These are all the poles, and you see there are soft poles, and there are hard collinear poles, and then finite terms, which I have not written. And then I have a menu of counter terms, right? I just say, okay, so what will cancel these poles? Well, the integral of this. And what will cancel these poles? Well, the integral of that. And then I have my soft counter terms, just by making the same sandwich with the other thing, and I have my collinear counter term in a similar way. I should emphasize that there are, so this is very formal, there are 2 problems. One is that this integral at this stage, it goes up to infinity. So I have generated ultraviolet divergences in doing that. And this doesn't matter in the sense that, of course, the infrared divergences are correct. So I can, for example, put simply a Fourier transform in terms of energy, put a cutoff there, and fix the energy, match it to the renormalization scale for the virtual, and it will work. It doesn't matter essentially how you do the ultraviolet. You could do it in dimensional regularization as well. And here, this is more delicate because, of course, L squared here is 0 because there is nothing in the final state, but L squared, which is the total momentum of the jet there, is not 0. So you have to match these 2 in order to actually sum them, and that's where the remappings make their appearance in this top-down approach, okay? And then once you have that, now I'm actually getting close to the end. Once you have that, then you actually have a subtraction formalism at next to leading order, which of course is the same as any other. We have not really developed this to the gory end, but we have verified in detail these things that I've been telling. Now, if you do this also at next to leading order, what you get, they are the completely unordered counter terms, right? You get, say, 2 particles that are collinear, 2 particles that are soft, and you get the complete double gluon radiation current, not strongly ordered. And you say, so what does it matter? I will just take the limit and extract the strong ordering. But this is not, we want a way to predict what happens when you integrate. And so what we do is build strong ordering. This is the strong ordering in history of the skyscrapers. And so we have to look at how this matrix element refactorize. And we have actually found something that we really liked. And then Stefano pointed out that something very similar was written by him and Ciafaloni 39 years ago, which is not a surprise. After all, these are, so they got a recursion, and we now phrase it in terms of Wilson lines and Wilson line correlators, but it's really the same thing. Okay? So anyhow, so if you look at the strong ordering limit of the double soft gluon current at 3 level, it is simple. And so you ask yourself, what does it mean at the level of these Wilson line correlators that we are? So I translate that by hitting it with polarizations. And so what happens is that the double radiative Wilson line correlator in the strong order limit refactorizes in a very simple and nice way, which is easily generalized. So basically what happens is that you have 2 gluons, and they're both soft, one is much softer than the other. So the harder gluon is radiated by the original configuration with n Born particle, in this case 2. But then this first gluon is much harder than the second one. So the second one actually behaves as if radiated by a system of 3 or n+1 Wilson lines, and you must notice that the color here is non-trivial. So this is an ordered product in which first you have this, and then the color index of this gluon becomes the entry color index of this Wilson line, and everything else here sort of is written. So we joke, sort of saying that gluons so far have been Regiizing, but here they are Wilsonizing, okay, because they become Wilson lines when you take this hierarchical. And this generalizes perfectly. So if I have 3 gluons and I decide they are all strongly ordered, then I can write the product of 3 matrix elements. So the first gluon is radiated by n particle. The second gluon is radiated by n+1 Wilson lines, because one has Wilsonized, and the last softest gluon is radiated by n+2 Wilson lines. And when you compute that, of course, you get the result that was also obtained by Stefano and Dimitri Colferai and possibly others a couple of years ago. And one can also decide to cluster. I want N1 gluons extremely soft, N2 gluons only soft, and 3 gluons, so only softish, and you would write something like that. So this factorization is very useful because of the following reason. And now I'm sort of essentially finishing, because I will give you only the soft. So if I had to guess in this approach what is the soft real virtual counter term, I would just say let's sandwich the Born with the 1 loop, 1 radiation soft function. And that's a natural candidate for the soft RV. But then I would look carefully and say, wait a second, this thing will have some collinear poles, which are not really supposed to be in the soft sector. And also I have this problem, and I want this thing to have the poles that cancel the integral of K12. So I go back and I look at K12. But now, K12 is exactly this strongly ordered soft function in the proper sandwich. And this, I have now shown that it factorizes into the product of 2 pieces. This is the cross-section level. So here's the amplitude, here's the complex conjugate amplitude. And if I look at this combination in between, this is the cross-section level soft function for n+1 particle, 1 radiation at 3 level. And then the second, or if you want in order of strength, the first radiation is sitting out there. And I need to integrate over K2. So then I can invoke my completeness relation, as we call it, just for this, and leave K1 standing without touching it. So the radiative, sort of the phase space integral of this object here over K2 will have poles, and these poles will be canceled. This is 1 radiation, 3 level, will be canceled by 0 radiation, 1 loop of the same object. And then I have a guess for KRV, right? That will automatically cancel the poles. So KRV is now the same structure, but here, instead of 1 radiation and 0 loops, I have 0 radiations and 1 loop, which is an object that I can compute, right? And the question is, so which one is right and how do they differ? And remarkably, the soft poles are actually the same, as they must, because otherwise it means that my argument fails. And this you can understand if you go back to the idea of a top-down approach, and you take more seriously this idea of refactorization and you bring it to loop level. So the idea is that one can take the radiative soft function, so this n hard particle and 1 radiation, and just consider it as an amplitude, right? And you see this is to any loop order. So scattering amplitudes factorize like this. And if I consider this as an amplitude in the presence of some external sources represented by the Wilson lines, it will have a jet factor associated with the extra gluon, which is the new leg that I have added. It will have a soft set of poles involving n+1 Wilson lines. So this is like the soft function of the soft function. And this is the hard function of the soft function, okay, so to speak. And these are the jet functions of the soft function associated with the extra radiated legs, which is the only one that I'm looking at. So if I now expand this to 1 loop, I get the normal combination. I don't keep the finite part. So the 1 loop can be either on this or on the jets, and I get this combination here. And now if I go to cross-section level, I get exactly this, plus some purely hard collinear poles, which they are the ones that I was afraid of. So if I just want soft poles, I can either use this and then subtract the hard collinear, or directly use this particular combination here. And because the soft limit of the real virtual matrix element is known explicitly for any number of particles, then you can just go and do some non-trivial color algebra and verify that indeed this is exactly what happens. And then in a slightly more complicated way that I don't have time to cover, you can do the same for the collinear configurations. And also there, so in the collinear configuration, very quickly, you have a guess for KRV, which is the radiative jet at one loop. But then you start realizing this will have soft poles, and not only given by the iconal jet. But there is a refactorization of the double radiation in the strongly ordered collinear limit. So if I want to radiate, say, 2 gluons, this is in the abelian limit, it's simple from a quark, I can radiate first, and so I first radiate one particle, and then the pair which gets radiated at the second level is much closer. And then in this limit, things factorize, just like it happened in the soft case. And then I can use a completeness relation to make a better guess for the collinear counterterm. And then again, you ask yourself, how are they related? And they have the same collinear poles, but they differ in the soft sector. And if you do the refactorization game that I just discussed, then indeed you get a difference, which is a soft function with 3 legs, because you have the Wilson line, the gauge Wilson line, the Wilson line associated with the particle that you started with, and the Wilson line associated with the radiation. One does not need to worry about collinear factorization, because this you need to take in the collinear limit, and the soft function becomes a singlet. So it's not actually a matrix. And in this way, if you work this way, which we have not fully implemented, but now we have a proof of principle, this cancellation of poles between the integral of K12 and KRV is automatic. But you have to be a bit careful about adding and subtracting, right? Not double counting the pieces that are present in the soft and in the collinear. Be careful and count them only once. So yes, so the outlook is very nice, as you have probably checked from Piazzale and Michelangelo. What I'm saying is that for infrared subtraction beyond the next reading order, where nothing happens, you have to understand, not only compute, which is not difficult, but to understand the strongly ordered infrared limits. Factorization provides a definition and also a computational procedure for soft and collinear kernels to all orders. They are expressed in terms of matrix elements of fields and Wilson lines, and in strongly ordered limits, they refactorize into lower order matrix elements, which are therefore known. This refactorization reproduces results that are known, in some cases since many years. And once I know that there is this refactorization, I can use, quote, completeness relations to link the K12s to the KRVs. Then you still, in the collinear sector, you still have to implement phase-space mapping, check for consistency, but the cancellation of the real virtual poles can be checked. And of course, all of this chat, in principle, smoothly generalizes to higher orders. Everything that I have shown can be done. Gets, of course, more complicated, but also at higher loops. So the architecture, I would say, of infrared subtraction is becoming clear. The building, like all buildings that are designed by expert architects, will take a long time. The actual building. Thank you.
Okay.
I see Sven yes. Moving.
Okay. No, I'm coming.
Yeah, very nice talk. So you had the RV and then you had the RVV now in the cubed LO subtraction. Do you see some structure in these? This would be one loop soft current, two loop soft current, so on and so forth. Do you see some structure based on this infinite factorization that you have?
I mean, C is a big word. I expect some structure. So let's look at soft, for example. So I expect this to be correct to any order. So if I want it at two loops, then there will be this thing at two loops. Then there will be this slightly complicated, I mean, the ratio adjusts itself to take away one soft and two soft in a nice way. So there will be a formula with, say, 6 terms or something like that. And I expect that to be correct because this is just saying, I'm just saying this is a scattering amplitude. I'm really not saying anymore. One has to be slightly careful because, of course, here these are poles. And here I cannot, now I have not discussed finite bits, but I cannot throw this away, right? I have to keep all the 1/k's that are finite, but I will need to integrate them. So this stays, but for now I'm only concerned with pole cancellation. So I expect this to generalize smoothly, generating a certain number of terms. And the collinear is rather similar. So an amplitude level jet factorizes in this way, and I have no loop numbers here. I expect this to be true. But I should at the same time emphasize that if I go back, I have to go back a lot, forgive me, but if I go back to this formula, so L1 is a sum of 3 terms, right? Before you factorize anything, before you sectorize, right? Then when you sectorize, it's many more. L2 is a sum of maybe 30 terms, right? Because instead of 1 minus S, 1 minus C, you have 1 minus S, 1 minus C, 1 minus SS, 1 minus CC, as Massimiliano well knows. So roughly speaking, it's 2 to the 5th, right? Then you sectorize, it's many more. So it's like 50. This thing here, it will have a few hundred terms, right? Yeah, it's hard. Wait, maybe you should.
Yes.
Actually, in your answer here, Lorenzo, you said something that made me curious. The soft and jet functions, we normally define in minimal subtraction so that they have only poles.
Yeah.
But you have in these radiative soft and jet functions also finite contributions.
Yes.
And you also have terms that are suppressed by powers of epsilon that appear there, like a hard function in an amplitude. If we treat you said it's like an amplitude. So if I just go with that, then I would assume that we need also to include positive powers of epsilon as well, not only finite.
I haven't thought much about that because I was more worried about finite bits in K. So what we are sort of planning to do with
it's singular both in K and in epsilon.
Exactly, and that is really what makes things complicated. So this thing here, it definitely. I mean, if I were to compute it exactly, it would certainly have pieces of order K, for example, and those we throw away. I don't think it will have pieces of order epsilon, but if it does, we also throw them away at this stage. At higher loops, then
my feeling. So I don't know how to make it consistent while throwing them away. So of course we would like to do the same generally in amplitudes.
Yeah.
And there's some context in the energy limit. We have essentially done that. We've only kept the hard part. But generally, there is this interaction in dim reg between singular poles and positive powers of epsilon.
So interestingly, for subtraction, except for a technical difficulty that you have to tell to the people who generate the one loop matrix elements, it turns out not to be true that you need the order epsilon and epsilon squared of the one loop.
Good, that's very good.
You don't.
Yeah. That's very good.
However, it depends in a sort of a bit of a subtle way in how I have to ask somebody to generate them, and then they have to sort of be careful that they do it in a way which is consistent with my minimal subtraction. But except for that, this was actually a paper that was written by Stefan Weinzierl more than 10 years ago.
Okay, yeah, I think I know.
He showed that you don't actually need the order epsilon and the order epsilon squared.
Yes, in principle, this should
problem.
be correct, but in practice, how to implement it, that's a different story.
No, I mean, it's a good point. I don't have a definite answer. I just have an expectation.
So further questions, comments? Yeah, so maybe sorry,
And I always ask you the same question, but
Yeah.
so did you ever try this, how it works next to living order concretely for a concrete calculation till the end?
Yeah, so now the answer is, although we don't have an implementation, but this is what I was very briefly saying at some point here. So this is a true statement, and when you try to actually do the calculation, so you have the iconal here, you integrate it over the soft phase space, literally just a single particle phase space. And then if I just use the definitions blindly, the integral goes to infinity, so there is a UV pole. I take care of that with a regulator of my choice. And the result is that the infrared pole that remains indeed cancels the infrared pole of this thing. And in order, so there is, of course, there is a 1 over epsilon squared here. So when you go to the 1 over epsilon, it has a log. And to cancel that log, you also have to match the renormalization scale that you put here with the cutoff that you put there. So in some sense, you cut off at the same scale. And then cancellation takes place. Here, I should rewrite this differently because it's a bit more complicated. So here, you have a glaring problem, which is the fact that when you have a jet function with no radiation, with L, I label the total momentum going into the final state. So here, L squared is 0 because it's a cut propagator. Here, L has become P plus K. So L squared here is not 0. And so if I want to actually play this game, I have to reparameterize, so use say Catani-Seymour remapping or some remapping, so that I bring both terms to be written in terms of an L squared equal to 0 plus radiation. And then we have actually done the calculation and we cancel the poles. So it is, so we had been writing very formal things, but now we do have a calculation. And of course, it's not a full implementation because I have just been canceling collinear poles inside the collinear sector and soft poles inside the soft sector. But yes, it works. Delicate, but it works. And in fact, I mean, if I may, it's true that we have a working subtraction and we expect to have a working subtraction also for the initial state soon enough. But what we have now in the bottom-up approach will not be doable at next cube if we ever tried, simply because of this problem of checking mappings sector by sector and checking consistencies. I mean, we have had to check of the order of, say, a couple of 100 conditions, which we discovered along the way. And at next cube, it would be a couple of 1,000, probably, right? So it will require more people than even Zurich has, or very large computers. So we need to improve, right? And this is where I now think that this top-down approach will actually, for a number of reasons, which we don't have time to discuss, will actually help.
Further questions? So maybe I have one. So
You have more than one. But
I have more than one, but still we have roughly 15 minutes until coffee break. So okay. So this top-down approach, I think this is more gearing toward the future, right? So NQ-BELO, because right now, if I'm not mistaken, in your current paper, the December paper, there's this delta term, and that's basically introduced to compensate for this mismatch of the pole structures, right?
Correct.
So what you are showing here is an alternate modified version where
Yes.
this is actually by construction cannot happen.
Exactly. This is exactly what it is.
Okay, okay, thank you.
And,
Thank you.
and you know, when I go back and I look at the fact that at the next cube, this will have to happen in 4 or 5 different ways.
Exactly, exactly.
Then if I have to sit down and look for deltas, it's gonna be a serious problem.
Yes, of course, yes, yes.
So I want an automatic way to
Exactly,
get this cancellation so that I can plug it in and
exactly,
forget about it.
exactly. Perfect, thank you.
Yeah.
Okay, so questions, comments, remarks? If there's no one, thank the speaker again.
Thank you.